As thread programming has become more and more popular, the number of threads also has significantly increased. However, now the programmers have to deal with the creation of so many threads, assigning tasks to these threads, managing the threads and joining them to the main thread if necessary, removing the threads. All these are now becoming a burden on the programmer. So rather than the programmer taking care of the threads explicitly, now we're looking into ways of managing the threads by the system in an automatic manner, actually taking care of the threads implicitly. So implicit threading is now looking into ways where all these management of threads operation is achieved either by the compilers or runtime libraries rather than the programmers explicitly doing this. We will be looking into 5 methods that are related. These are thread pools, fork join, OpenMP, Grand Central Dispatch, and Intel thread building block. So let's first look at the thread pools. Now, one approach would be every time you need a thread, you create the thread, assign a task to the thread, take care of all synchronization, and when the task is complete, get rid of the thread. However, creating a thread every time you need it takes some time, though it's much faster than creating a full process. Still, it takes time. This becomes important when you need to create the threads, especially very frequently. So an approach that provides a slightly faster service is to create some number of threads a priori, keep them in a pool, and whenever there is a task to be executed by a thread, find a free available thread from the pool, assign the task to that thread so it's not in the pool anymore, and when the task is completed, the thread which was executing the task is not destroyed, but instead it's put back into the pool. This approach also allows us to keep the number of executing threads under control, because whatever your pool size is, the number of executing threads will not be able to exceed that, because when the pool is completely empty, which means all threads that have been created are already executing other tasks, and a new request arrives to find a thread for a task, but there is none, that request will be kept in the queue. Whenever one of the executing tasks completes, so its thread becomes available, it will be returned back to the pool, and whenever a thread is added into the pool, it will check the queue to see if there are any pending requests, and it will find such a pending request and immediately serve this one. This way, as I said, the number of executing threads will be bounded, will be under the control. Also, this way we are separating the task to be performed by the thread from the mechanics of managing the thread, creating the thread and then destroying it, whatever. So this could be, for example, providing us additional opportunities, more complex uses. Like, for example, you might want a task to be executed, say, in a periodic manner. For example, you say, execute me this task, say, in once every 15 minutes. So rather than dealing with setting up alarm clocks and restarting the task every 15 minutes, this thread pool will provide you the functionalities for that. Or, for example, you may also want a task to be created and executed at a specific time rather than immediately at the moment. So thread pool is providing us all these functionalities. An alternative is fork join, which is actually a synchronous threading strategy, available also in Java. So there is a library that takes care of the creation and joining of the threads. But this fork join is suitable for a specific class of problems, specifically the divide and conquer class of problems. Remember divide and conquer problems. A very good example of this, for example, would be sorting or searching. Like remember binary search or quick sort algorithms. You have a huge data set, and rather than trying to sort or search in this huge data set, you split it into multiple parts, let's say simply into two, and you attack these subsets individually. Those subsets could still be large, so you split it further into two for each one, and it continues in this manner. So it's just like what you see in this graph. You have a task to do now, and you split the task, which implements your problem, into two smaller tasks. In other words, it will be actually creating two threads to handle these smaller sub-problems. If those sub-problems are still too large for the task to complete, they will be further divided into two. And it may go this way as much as you want. As you will remember from divide and conquer problems, if you go all the way down to a subset of a single element, the number of levels you will have in this tree would be log base 2 of n. But typically we don't need to go all the way down to the simplest case where we have a single element. When there is a small number of elements which can be handled by the task, by the thread, it doesn't need to further divide. It will just, since it's a small portion now that it can swallow, it will just take care of that small subset of problem, solve it, and return the result with this join, because actually when this task is completed, it's trying to join to the thread that created it. Similar is true for also for this task. That will also try to join. Now this task here, which created these two subtasks, will take these joins and merge the results, and that will be the result of this overall task. Similar would be done in here. So this one would also have the merged results of the smaller two tasks. Now the result of this task and the result of this task can be merged at the task that created it when these two tasks join to the creator thread. So this is the basic idea how fork join system works. The third alternative is OpenMP, which actually is a set of compiler directives and also an API library, which is used in typically in C, C++, and Fortran. So this is not a full standalone system. This is just a library. So when you compile it, it becomes part of your program. So OpenMP provides support for parallel programming in shared memory environments. That means in systems where the cores have access to a shared memory system. With OpenMP, you're identifying parallel regions in your code. So it's not like your whole code is executed in a parallel fashion, but in your, for example, C code, for some part you say, execute this part in a parallel fashion. So this is, in other words, my parallel region. So we're creating blocks of code that can be run in parallel. And to do that, you make use of this pragma. if you have never used pragma in C or C++ earlier, pragma is a compiler directive. Just like, for example, include in your program, or for example, defines for defining constants in C. These are actually compiler directives. A compiler directive works as follows. When you write a program in C, when you want to compile it, actually before the compiler, we have the pre-compiler working. The pre-compiler opens your source code, and it will find these directives, where each directive starts with a hash sign, like the hash sign in front of include, the hash sign in front of define, the hash sign in front of pragma. It will handle only these. The pre-compiler does not look at the rest of the program. It just finds the directives and it does what that directive says. For example, in the case of include, this sharp include omp.h means go and find a file named omp.h in the list of include directories defined by your compiler or your environment variables. Find this file, take the contents of this file, delete this include line, and replace it with the contents of omp.h. It will do the similar, for example, for stdio.h. If there was, for example, a sharp define definition, let's say for pi, defining a constant as 3.14, it would, in the rest of the code, whenever it sees pi, it would just do a replacement for pi with the value 3.14, or similar for macro calls, whatever. So similar thing, when your compiler sees this pragma, it will find the beginning and end of the block, and it will say this part is to be treated in a different way. How it should be treated by the OpenMP system. So, for example, if we have the code like this, we're including OpenMP header, standard input-output header. We have our main function. Here we could have anything. So the code there would be executed in sequential manner, just regular programming. So that part is a single thread. But when it comes to this pragma directive, it will see that it has to be handled by OpenMP. By the way, we use pragma for many other things, so you should say it's related to OpenMP and it should be executed in parallel. So starting from this open brace till the end of the open brace, it will take this part, the code segment here, and execute that code segment in a parallel fashion. What do you mean by parallel fashion? OMP, from the configuration of your system, knows how many cores you have. So it will create so many threads, and in the threads, it will try to execute that statement block in a parallel fashion. But when it reaches this close brace, that's the end of the parallel block, the OMP block. So the rest is again a single thread executing. In addition to such parallel regions, blocks of code that are to be executed in parallel, OMP also defines some specific directives, for example, for parallelizing loops, because that's the most commonly used piece of code, because each iteration could be, for example, executed on a different thread. So if you, for example, want to use parallel for in OMP, you say sharp pragma OMP parallel for, you should write for here now, and then you have your for loop, and in this for loop, let's say we have, let's say n is 10, and we have a quad core system. That means our CPU has 4 cores in it. Okay, in that case it would create 4 threads for us and execute the first 4 iterations in parallel. When they are done, it would be executing the next 4 in parallel. When they are done, it would be executing the remaining 2 in parallel in these 4 codes. It's OpenMP that's taking care of all of this. The fourth approach is Grand Central Dispatcher. Now, the Grand Central Dispatcher, GCD, is Apple's API and also runtime library for parallelization, used both in macOS and iOS systems. It provides extensions to C, C++ languages. It provides an API and also the library in the real implementation of the API. It allows identification of parallel sections, so in that sense it's similar to OMP. It manages most of the details of threading, so if you want to run something in parallel, what you do is you create blocks similar to what we did in OMP, starting with a caret, then anything between the open and close braces would be your parallel block. Like, for example, if you want to execute this printf statement in parallel, you would be just writing caret, open brace, your statement, and then close brace. These blocks are placed in what's called the dispatch queue, hence the name Grand Central Dispatcher. It's assigned to some available thread from the thread pool when it's removed from that queue. So when you make the request, it's first placed into a dispatch queue, and from the dispatch queue, when a thread in the pool becomes available, it will be automatically removed from the queue and be handled. Now, there are 2 types of dispatch queues. One is called serial, for serial, and the other one is for concurrent tasks. So for the serial, the blocks are removed in first out order, and this queue is per process. Therefore, it's also called the main queue, and the programmers can create additional serial queues within their programs. However, in the case of concurrent queue, again, it's processed in FIFO order, but instead of one by one removing the tasks from the queue, it can remove multiple of them, multiple tasks at a time, and run them concurrently. That's why it's called concurrent queue. And in the modern or the latest Grand Central Dispatcher, there are 4 system-wide queues for user interactive processes like graphical user interface operations, user initiated. So these are also initiated by the user, but user interactive processes are to be handled as soon as possible. User initiated are like one level down in priority. There are the utilities which are run typically when there is an opportunity, but they don't require interactivity, so that's why they can be delayed as necessary. And the lowest level would be background, for example, for things like synchronizing, say, your Dropbox, or for backup operations. For such things, we have no emergency, so whenever all other queues are empty, then you deal with the tasks waiting in background. Otherwise, you can delay them as much as you wish. There's no urgency there. And the final approach for implicit threading is Intel's thread blocking block, or TBB. It's designed for C++ as a template library to handle parallel applications. So it is a library that handles task scheduling and load balancing. So as a C++ programmer, you don't need to deal with those details. But while doing this, it is cache aware. That means, for example, when it is doing task scheduling and trying to decide which thread is to be executed next, which thread is go into the available core, it's looking at the availability of the data in the cache. So if it finds that another task already has its data in the cache, it might prefer that one. Of course, it's also looking at fairness. So the ones that don't have their data in the cache, at some point they will also get the chance. Otherwise, it will always be the ones that are in the cache, and they will also always be in the cache, so the others would starve. The Intel TBB supports parallel loops. It provides special data structures and commands for running loops in parallel. Atomic operations, that means you want to say, if you start doing this task, doing this, say, instruction, you should not cut in the middle of that. Okay, like for example, say you're trying to take the power of a number, a to the power n. So you either don't start calculating it right now, or if you start it, don't do a thread switch in between. Do it in an atomic manner. So it has some such atomic operations, typically used, for example, for modifying large records, because we don't want to start modifying part of the record, then having a context switch to another thread, and that thread, if it tries to access the same item, then the record is actually not in a stable state, because the beginning of the record has been updated, but not the rest. So these are atomic operations. When you're trying to access the same data item over two or more threads, then you'd better do mutex locking, mutual exclusion locks. We will be discussing them in the next chapter. So it provides mutex locking, and in general, it provides what's called thread-safe data structures related to actually mutex locking and atomic operations. It provides thread-safe data structures like hash map, Q, vector. This means the following. Some data structures, if they're handled by a single thread, there is no problem. But if you handle some data structures by multiple threads, then it is possible that one thread messes up with the other. Take it like, consider a linked list. Now assume that you're trying to insert a new element somewhere in the middle. Remember, you have to update several links. For example, if it's a double linked list, you will have to update 4 links. Assume that while one of the threads starts inserting the element, say between the third and the fourth elements in the linked list, between third and fourth, another thread also wants to insert something, let's say again at the same point, after the third, or maybe it's removing fourth, it's deleting fourth. Now you're trying to insert something between third and fourth in this thread. The other one is removing fourth. So actually, fifth should be having a backlink to the newly inserted element, but this thread is not aware of that. So it will cause a problem. So such data structures are said to be thread unsafe. That means it's not safe to use these structures with the threads. To make it thread safe, you should modify that data structure that will prevent such errors. And Intel TBB, for example, provides us such versions of hash map, Q, vector, and some other thread safe data structures.